All right, we're gonna do true, false first because sometimes that's the one that will get you on multiple choice. So forgive me, this is my handwriting. Yep, so if it's a little hard to read, it's just me. So 1 should be never true. You're checking with me right now with a different color pen. B, sometimes true, so ST means sometimes true. C, always. D, always. E, never. F, never. G is sometimes. H, always. 1, always. And 2, question 2. So I'm just going to kind of keep going in order, and it helps if I say it out loud, that way you can kind of look it over. 2, qualitative. B, quantitative. C, quantitative. D, qualitative. And then I'm going to let you guys check 3 for a second because that's a little bit more in depth. I'll leave it right there. See where you are. If you can't read something, let me know. Can I scroll past 3? Give me a thumbs up if you're okay looking at 3. If you're done, so give me a thumbs up if you're done looking at 3. Okay, still keep looking, please. Alright, I'm going to scroll to 4. I can go back to 3. So this was the one we practiced more Friday, and if you weren't here Friday, there's notes online from Friday, there's videos from today. But this is the one a lot of you guys were finishing up in class, and so you were just practicing rounding to the correct suffix. So 4 is 435 milliliters for A. B is 25,000, no decimal. C should be 210 centimeters squared. D, 7.69 centimeters. E, 39,452 kilograms. F should be 73 centimeters. G, 9,060 meters. H, 1.4 times 10 to the 9th kilometers squared. My handwriting says squared. I, 10 point, so the decimal holds in place, so there's 2 sig figs there. For I, centimeters. J, 14 kilometers. K, 0.0280 millimeters. So how many sig figs are in K? How many? Loud and proud. 3, because that 0 in the front is kind of just a placeholder. You don't start counting until you get to the 2, 8, and then the last 0. So those are the ones I definitely wanted you to have a chance to double check, because you're just rounding to a number that would be truthful to what you know. All right, I'm gonna look down at 6. No, 7 actually is the one I wanted. Who got 7? 480, no decimal, centimeters cubed. Just give me a thumbs up. It's right in front of your chest. The whole world is going to see. It's me. Usually very few people actually get it right because you've got the whole process like, I can multiply, I got this, and then you forget to do sig figs. That's really it. So the practice that we're practicing today in our lab is practicing sig figs with measurement and then calculating them correctly. So we multiplied all these together. We got 483.12 centimeters cubed. You probably were like, check, got my units and everything. But then you forgot to go back and do multiplication, means count sig figs. This was your limiting factor of 2 sig figs, so this needed to be rounded down to 480. And it was still centimeters cubed. So that was one just to make sure you can apply it in new situations. This rounding one, take a minute and check those because some of us struggled with that Friday. Yeah, it's helpful just checking a different colored pen because then you can only, like, you just study the things you got wrong or revise the things you got wrong so that you have a chance to see where you know, how well you know what you know. Okay, so some of you guys are staring off into the wilderness. I want you to write at the top of your problem set 2 things that you need to work on. Maybe they're really minor, like you got the whole thing right and you're awesome, or write down 2 things you can work on. Be very specific for yourself. Maybe you need to work on adding and subtracting rules. Maybe you need to work on just simply counting sig figs. Maybe you need to work on the rounding line. Maybe you need to work on true-false section because that's like, oh gosh, I got to read the textbook for that, or look into the textbook more in depth for that. So just be specific for yourself. Hopefully you've had a moment to reflect on kind of where you are, because you might be in different places, or someone else might be like, oh, I can help you with that. A study buddy is always a good thing for chemistry, because then you hold each other accountable. I have a lot of people that like to meet at Panera, Chick-fil-A, FaceTime, whatever, just to have something to, you know, have somebody to bounce ideas off of, okay? So we're going to do our lab in about 10 minutes or less, okay? So if you'd like to continue your notes on the same paper you've been working on, if you'd like to redate your papers and, you know, start fresh each day, if you have a little composition notebook and that's how you're going to roll for the whole semester, do what works for you. But your job is to try to keep all your Unit 1 notes together, try to keep all your Unit 2 notes together, and then so forth, okay? So density is our topic of today, and it's our lab for today. You can see today we are looking through problem set 3A, density intro, and then the lab, and we might have time to talk about dimensional analysis at the end of the class. So I'll let you write down some vocab first. You do not have to write this word for word, but the idea is that you have a general understanding of the main differences between these 4 terms. Raise your hand if you are familiar with density. Like, you kind of know what it is. Okay, so a couple hands go up. So density is a derived unit, and that's something you watched on one of your first ed puzzle. Derived unit simply means that it's not just a single unit. It's not just grams or just milliliters or just meters. You derive it, meaning you calculate it. Many times that is going to be us taking mass and we'll divide it by, so like we'll do a calculation, divide by what to get density? Volume, good. And so you'll notice I use the generic terms for those two measurements, mass and volume. I didn't give you the units, but what's the most common unit for mass? Grams, good. And what's the most common unit? Well, there's two, but what's a common unit for volume? Say again? Meters cubed, good, that's one. You can also have grams per centimeter cubed. And then there's one more, using like liquid volume. Liters, okay, I'll go with that. Or the smaller version of that, milliliters. Okay, the one that we will likely use frequently is grams per milliliter or grams per centimeter cubed. Because we're not dealing with like liters of acid and liters of water at a time. We're dealing with small amounts, so that we'll use those smaller versions. So those are the two units of density that we frequently use. So density is just a derived unit. I mean, we have to take the matter, the mass, and we see how much space it takes up, which is the volume. So we do a comparison between that. Fun fact you should know now is water, H2O in its liquid form, is going to be the density of it is 1 gram per 1 milliliter, which is a total of 1 divided by 1 gram per milliliter. So 1 gram per milliliter is the density of water. So that is something I expect you to know now. And that's what we do, we compare a lot of things to water. So yell out something you know that sinks in water. Say again? A brick, what else? Say again? A marble, what else? Somebody from the back. Say again? Turn, what you got? A rock, right? So all of these things that we've named, a brick, a marble, and a rock, are they less dense than water or more dense than water? More. So more dense means essentially we have water, okay? I'm a picture person. I think it helps to visualize these things. So here's a bucket of water, okay? And here's the water particles. Now they're a lot closer actually, but we're dealing with like super nanoscopic things. So there's water, right? Okay, so do you see all these particles are spaced out? How would you say a rock's spacing would be? Would the particles be close together in a rock or far apart in a rock? So say it louder and prouder. Very close, right? So a rock will be super, super, super close together, which is I'm trying to indicate to you that it has a lot of matter and a little bit of space. So what am I trying to indicate to you? It has what?
Higher density.
Yeah. So it's highly dense, meaning that has a lot of particles per space. So what's this rock going to do eventually in water? It's going to sink. So the particle diagram here that I've kind of shown might be something to visualize when you're thinking about density. Questions here so far? Yay or nay? Nay, okay, remember I'm not a moderator, so you got to respond regardless. Okay, actually I want to show you this video first. There are like 5 facts that this video goes through. I want you to write down those 5 facts. It doesn't have to be extreme detail, but something about it would be helpful. Oh, I already had it. Oh, well, we're also going to turn off Pandora real fast. Okay.
A can of Diet Cola.
Okay, here we go.
Density, thanks. A can of Diet Cola will float, and a can of regular cola will sink when placed in water. You see, in the same amount of fluid ounces, there are more atoms in the can of regular cola. The main ingredients in cola are carbonated water and sugar. So each can has the same amount of water molecules, but in the same space, the regular cola has additional molecules from the sugar. Putting more atoms in the water forces the molecules to be more dense, making the cola sink. Hot air balloons fly because of density. Just like all matter, air is made up of atoms and molecules. When air inside the balloon is heated, it expands or gets bigger. So compared to the air around the balloon, the atoms inside have more room to move around, and as a result, are not as tightly packed together. The air inside the balloon is less dense than the surrounding air, and the balloon becomes buoyant. When it's
Oh, okay. So, just fun fact: who's ever ridden a hot air balloon? Anybody? Gosh, you guys are special. My husband won't take me. It's too expensive. Okay. So, basically, they're talking about air moving apart in what kind of conditions inside the balloon. What's going on in here? It's hot air, right? Who's ever heard hot air rises? Right? Why in the world does hot air rise? It's a weird thing. It's less dense, so it moves up above the more dense air that falls to the bottom. So if you have a problem with like heating your home, it might be hotter upstairs or hotter downstairs based on the season. But hot air truly rises, so if you heat the bottom, first floor of your home, it still will rise to the top. So my image here has my particles spread out a whole lot in the hot air system, but then the atmosphere outside has the particles pretty well consolidated. They're dense. So what's eventually going to happen to this balloon? It's going to go where? Up and away, right? It's going to keep floating until it meets its same pressure system on the outside, so the same density on the outside.
It's time to land. The pilot stops heating the air, and as it cools, it contracts to match the density of the surrounding air. The effects of gravity go to work and bring the balloon down to Earth. If an object is cut in half, its density remains the same. Take a look at a gold coin, made of neatly arranged gold atoms. When cut in half, the tightness of the atoms does not change. Whether you have a half of a coin or a complete gold coin, the density stays the same.
So they didn't say the word I wanted them to say here. So if you have 1 drop of water, what's the density of that 1 drop of water? 1 gram per milliliter. If you have an ocean full of water, tons and tons and tons of drops, right? What is the density of the ocean of water? It's the same, 1 gram per 1 milliliter. It's called an intensive property. Intensive, meaning it's an inherent property. Inherent means like it's a natural property about the substance. It's not going to change based on how much you have. If you have 1 versus a million particles, the density is still the same no matter what the amount you have.
The density of liquid water is 1. Objects with a density of less than 1 will float, and objects with a density greater than 1 will sink. Take a look at these 3 objects. All of them float, so their densities are less than 1. But if you take a closer look, you see that as density increases, more of the block is below the waterline. Scientists have figured out the density of a block converted to a percentage is equal to the amount below the waterline. For example, if 75% of a block is below the waterline, its density is 0.75.
So that little chart or the diagram he showed right here, this would possibly be useful for some engineer who's trying to make sure that their stuff is not going to tip over in a pool of water, it's not going to sink. So think of a boat, right? How much of a boat's like the mean for like a cruise liner? Think of like that. How much of that's underwater? What do you guys think? Like 50%, 100%, under 100% would be in bad shape, right? So how much of a cruise ship's like underwater? Yes. 40 to what? 10, 15? I feel like 10% would kind of teeter-totter and possibly fall over. But I mean, those are huge, so 10% is a lot. So maybe like 30 to 50%, I have no idea. But the goal there for them is to make sure that their density of their cruise ship is displacing enough water so it doesn't sink or it doesn't teeter-totter and fall over.
Converted to a percentage below the water. When water freezes, ice float, its density is 0.75. Ice floats because of density. When water freezes, it expands. Just like the expanding air in the hot air balloon, water molecules in expanding ice spread further apart. The atoms in ice are not as tightly packed together as they are in the liquid phase. If we observe an iceberg, notice about 92% of the iceberg is below the waterline. This means that the density of ice is 0.92.
Okay. So, we turn the light back on for me, one of you guys over there. Appreciate it. That last part where they talk about water's liquid to solid phase, ice expanding, that is not true for everything else on Earth. Ice is water is actually a really unique substance. So ice expanding is an anomaly, meaning that's not normal. But we know we know it exists because we deal with ice every day. So ice expanding is not normal. Everything else on the planet, solids are more dense. Hence why you guys all named off all those substances that were solids, brick, marbles, rocks. They're all solids, and they're the ones that actually sink in water. They're more dense. So ice is a weird guy. It's not normal for it to do that. Okay, so we're gonna do like 2 or 3 calculations of density using like experimental data, and then we'll actually go to our lab and do that, and we'll make sure that everybody's on the same page with sig figs. Okay, so from a word problem, please do not write down the whole daggone word problem. It's too much. So what we want to look for are the most important pieces of information we need. So Bailey, give me one piece of information that's important here on the first one. Okay, so we all want to write this down. This is what we write. M, how did I know that was M, meaning mass? Okay, so it says the mass, so that's your first clue, and then it says grams, which we know is the unit of mass. So there's 2 parts that can help us there. So mass is 152.2 grams. Okay, sorry, I'm still cheating. Estes, give me another piece of important information.
The length and width of the solid.
Okay, so I'm just going to write those separately. Length, width, 3 centimeters each. Admir, give me another. Oh, sorry, actually lies. Oh, no, yeah, give me one more.
The height is 2 centimeters.
Okay, so H, 2 centimeters. Okay, and here we go. We've got lots of data. The question says, what's the formula for density? And then literally wants us to calculate from there, right? So, Ariane, what's the formula for calculating density? Right, so density is equal to mass over volume, right? We've got mass, check, so we're good to go, right? Maverick, how would I get volume from here? Okay, so the length times width times height, length times width times height gives us volume. We know that from what, like 9th grade, 8th grade even? 7th grade? Plus kindergarten, right? Okay, so we know how to approach this problem quite well, it looks like. Okay, so here we go. Density is mass over volume, so mass 152.2, whatever, 5. Put your units on this as well, guys. In math class, they run around obscene with naked numbers everywhere in math. We like to have clothes on our units. We put like grams and centimeters and so forth. All right, so the density, or the length times width times height, is 3 centimeters times 3 centimeters times 2 centimeters, which is what? Okay, so you can do 3 times 3 is 9 times 2. You don't need a calculator for that. So I know I'm going to put 18 centimeters. What? Cubed. That's what I want to put. But let's think back to sig figs. If I do this multiplication action here, what should I really be reporting that to? How many sig figs?
2.
Look, I got a 3, and I got a 2. What's my limiting here? 1 sig fig. So I want it to be 18 because that's pretty accurate, right? But truly, I'm not allowed to. What should I be writing this as? Not 18. Any takers?
2. 20.
Or I could do scientific notation, or I could just put 20. I'm going to be lazy and just put 20. So truly, I know that this should only have 1 sig fig. Now, I'm not going to change my value up here because this is simply like how I'm going to finalize my answer. Simply like how I'm going to not lie to you about my final answer. Because is this my final answer? Is this my final answer? No, so I can be incorrect in my sig figs in the calculation side of things, but my final answer should be correct to sig figs. So when I multiply these, I'm like, okay, it should be 20, so it should be 1 sig fig, but I'm going to go with my non-rounded answer so I can actually calculate from here. So I'm using the non-rounded here. So what's 152.2 divided by 18? 8 point what? 4. Give me more.
So it's 5.
So it's 5 repeat. Okay. So I'm going to write that just so we're on the same page with that calculation. And that's grams per centimeter cubed. Okay, so this is my calculator answer. 8.45555 grams per centimeter cubed. So, how many sig figs, knowing I'm dividing here, I'm still looking at sig figs, how many sig figs should be my final answer? 1. It's stupid. We had a really horrible ruler, guys. I couldn't help it. Because this has 4 sig figs, and this should have 1 sig fig. So the 1 sig fig rules the roost. So what should this be in terms of 1 sig fig? Just 8. That's it. 8 grams per centimeter cubed. So what piece of equipment would I reconsider using next time? A better ruler, right? So the mass was great. Like, we had a fantastic scale, but the ruler was crap, and so that limited our accuracy in the measurement, which limited our accuracy in deciding upon the density. Are you see how we're fitting all this together now? The sig figs matter, and it's simply so we're not big fat liars. Okay? All right, so decide on how to attempt 2 with the person next to you. You're good to go. You go. Just let you think first. I see a lot of negative numbers. Come on, people. Where can you make? All right, Anne, come back to me. So hold those conversations for a moment. Thank you. Riley, give me some important information here. Okay, so M mass is 45 grams. And that was how many sig figs here? 2 sig figs. We are not going to have to write that every single time, but I'm just thinking out loud here, okay? Camilla, tell me something else that was important and maybe how you approached with that. Okay, so in the grad sil, right, in the graduate cylinder, it was originally 60, right? And then keep going.
And then it rolls.
Okay, so it went up when the rock or something, right, was placed in it, up to 75. This cannot be to scale, but here we go. Okay, so it went up. So what does that really tell me between the lines? Well, the height in a situation where you've got water, the water's moving because we're plopping a rock in here, and the rock is taking up space. So when I say take up space, what is the vocabulary that comes to mind? Volume. That was just literally a definition we wrote down. So taking it, or the amount of space you take up, is the volume that that particular piece of matter has. So Cole, tell me how you would approach this change in volume, or this change in height, I'll say. What is that really telling me here? Not the density. So the rock went in, the volume went from 60 milliliters to 75 milliliters. So what was the change here? 15 what? Milliliters. And everybody, milliliters is a unit of what? Volume. So there's little clues to tell you that this is volume. 1, you're talking about a graduated cylinder, which measures volume. 2, unit is in milliliters. This is volume. This is not density, nor is this density. But this volume now, being 15 milliliters, is something important to us. So Kern, how would you approach this to now solve for the question of what is density? Say again? Nope, there's actually, so let me get back up here. So we have a problem here that dealt with a rectangular solid. So we had a rectangular solid, and we had length times width times height. So that was how we had to find volume, and that was like geometry. We actually had to mathematically calculate. Down here, we don't have a rectangular solid. We got this irregular object of a rock. There is no length, there is no width, there is no height, because it's like a little blob. So we use something called water displacement, which I thought it said, yep, here. Water displacement is another method of determining volume. So raise your hand if you can tell me how we're finding density from here. Yes, ma'am.
45 milliliters.
Okay, so density is still mass divided by volume. Once we get mass, once we get volume, we simply divide. And then 45 grams divided by 15 milliliters. You can do that in your head. What's 45 divided by 15? 3. Okay, good. So I'm going to write 3 because we just like, oh, calculated. We got 3 when you put grams per milliliter. But then you go back and you say, okay, total sig figs here is what? 2 sig figs all the way. So I need to modify this to be more accurate. So we would record it as Very good. And this is density of said rock. Okay, I'm stopping there. Pull out a piece of paper and call it density lab. So we will deal with regular shaped objects and irregular shaped objects. I expect you got a little bit of background on how to calculate volume of regular objects. I give you some tips in your lab though. So let me tell you the rules for lab. Now, I see looks like everybody has signed the safety contract. Okay? If you have not done the safety contract, you will not do lab. Plain blank. Like, it's a rule, and I'm a rule follower. So if you don't have your safety, like the paper form in the box yet, or you haven't signed the online one, you will not do lab. Now this, I'm calling a lab. It's an activity. We are using no chemicals outside of water. Okay, so you should be fine. You shouldn't get acid in your eye and stuff on your toes, like you're fine. But in the future, like we have 3 labs the rest of this week, 2 labs the rest of this week, you won't do lab. Okay, so if you know you've not done safety contract, note to self, you need to do that. So I've already checked a lot of you guys, and I haven't updated this morning because, you know, AP Chem was first and then you guys. Okay, so in terms of labs, you always write the purpose of the, there's a purpose when you're reading your lab. I want you to clarify what that is for yourself and for your lab group. So go ahead and write someplace underneath your title purpose, so you don't forget that you have to write the purpose of a lab every single time, because it's nice to know like why we're doing an activity or why we're doing a lab. And I'm giving you an inquiry lab. Who's ever heard the word inquiry? Not, so inquiry can just mean a question, like I have an inquiry, I have a question. But it also can mean you have to think about what you're doing, and I'm not going to hold your hand the whole time. Not all of our labs are inquiry labs. A lot of my labs are like, do this step first, do this step second, and so forth, because you know they're involving chemicals that can be hazardous. But what I'm telling you for an inquiry lab is you have to like kind of process how you want to attempt this, because there's many ways to go about it. But I'm giving you like 8 items, so I'll give you 6 to 8, but I'm giving you 8 items, and your job is to determine the density of each of those items. You have all this equipment that you can use. It's up to you on what you want to use. You know what's in the drawers, you know what's in the cabinets. So your job is to determine the density. So you can't just straight up determine density, can you? Like I don't have a measuring device back there. It's like, oh, let me just measure this. Yep, that's the density. So what should I be using to determine density? Maybe a scale. So a scale's gonna give me what? Mass. Okay, and then it's up to you to figure out on what you would like to utilize to determine the volume. Okay, so we know really I'm asking you to find mass and volume, but then collectively those to go together to find density. Okay, you need to make your own data table. A lot of times I give you a data table to fill out, but this go around I want you to like make your own data table. Organize the items at the very end. I want you to determine the density for everything. Organize the items in increasing density, and then take a picture. One person from your group, please, not all 30 of you, okay? So one person can take a picture and send me an email with the picture, and that will be like kind of one of your concluding questions there. On every lab, there are usually analysis questions, this lab included, so there are just a couple questions you'll complete after you've determined all of this. Questions here right now? Yay or nay? You gotta tell me. No? Okay. This is my reminder for you. You have rulers, right? And a lot of times you'll use rulers for regular solids and to help determine maybe their length, their width, and their height. So you always have to have an estimated digit. So if you measure this, you are not going to say it's 1, 2, 3, it's 3 centimeters, I'm good to go. You're going to have to make an estimation. So you'd say it's 3 what? 0.2, but somebody else at your table might say it's 3.1 or 3.3. So your job is to make an estimate and then go with it and move on with calculations. Okay, so there you have the same lab groups as last time. You may go and pull out your lab notebook. I'll help you when you get back there. Same lab groups as last time. Pull out your lab notebook. Scales are coming to your table in just a second. They're going back. So now I see no nobody with the Labrador out. Labrador's in the very bottom of your packet. You should see the last page. Cabinet number 4. So there's a binder, and instead of printing out 30 copies of a lab, it's good. So we're gonna open up the notebook. It's probably about 4 to 6 pages back, but you're looking for something that's titled Inquiry Density. Inquiry Density. Sorry. So one of this inquiry, yes, that's it, inquiry. And you are good to go from there. So keep it in here. Keep it together, okay? Alright, everybody just pause. 5, 4, 3, 2, 1. Eyes over here. Pet peeve, okay? This top of the balance is not always secure. Do not turn to the side or upside down because it's going to decalibrate it. Okay, so you're going to take your AC adapter, plug it into the back, there's a little plug in the back, plug it into the outlet, and then you're going to turn it on. Give it like 3 seconds because it takes a minute to kind of get itself up and booted. And then from there, you're going to zero your scale out. Zero it means that there's no like weird number there, so it'll be 0.00. Now my scales are a little haunted, so the vibrations in the room and me talking even can cause some fluctuation. So if you'd like to go and do that now, get to the 0 mark. Get it zeroed out. Okay, so maybe yeah, they look maybe Alright, and you're good to go. You need to do data tables so you can figure out what you're measuring, and then do a little divide and conquer. One person in your lab room turn this way. One last lab member turn this way so I can look at your eyes. Okay, so some of you guys have gravity cylinders that are small, medium, and then these are the large ones. They're not as accurate, but if you have something that will not fit in a normal grab sill, you see this one's got a large mouth, so you can put something larger in there. The frog, okay? So do not put a regular object through water displacement. Regular objects have a regular way you can find their volume, yes? And I have tips for you on your paper. So don't put a cube in here. Do not put a cylinder in here. You have methods to find their own volume. So I'm just going to leave these here wherever you need them. Some of you guys got farther than others on the analysis. You have your paper in front of you, still, right? Yes? Okay, so for the copper, a lot of you guys had copper cubes or a metal cube. And, sorry, I'm just trying to open another tab here. Here we go. And you had the opportunity to find the percent error. What was the percent error, or I'm sorry, what was the actual value I gave you in the lab? You guys write it down? What was it? 8.9, thank you. So 8.9 grams per centimeter cubed was our actual value. So this is like the accepted or the actual value. All right, so if you did not have copper, still write this question down with me just because we're practicing how to calculate percent error. Raise your hand if you had a copper cube. All right, Elizabeth, can you tell me the density of that copper cube for your group?
Oh, no.
8 point what? 54 grams per centimeter cubed. Okay, so this was their experimental data. So if you have your own experimental data, definitely use yours, but if you did not have a copper cube, this is the experimental data. Okay, turn and talk on how to calculate percent error. And actually try it, like actually do it if you haven't already done it. Okay, so at this point you should have had time to discuss and even potentially calculate. So in terms of percent error, you always are just finding the error, the differences between what you should have gotten accepted versus what you actually got, which is your experimental. So this group did a great job. There was very little error there. So what, 0.36?
Yeah.
0.36. So not bad at all. Good job, group. Then when we divide that, which is absolute value, because we never can have negative percent error, we divide it by our true value, which is the actual value. Multiply by 100, what's this percent error? Come on. Anybody calculate this one? The group that gave me this data at least should have. All right, I'll wait on you guys. Somebody calculate that right now for me, okay? .04. Can I get a second on that? Okay, if you are not calculating, this is not an optional exercise. This is something I want you to practice. So let me tell you why I'm having you do this. Because one, a lot of people are calculator stupid. They think the calculator does all the work for them, and it does a lot, but it doesn't do everything. It's user error a lot. So if you subtract and then don't hit equals and then separately divide, it may not calculate this. It may not do PEMDAS right for you, parentheses, exponential and everything. So you actually have to get the difference and then separately divide and then times by 100. So 4.04% is, I got a second on that, thank you very much. So this should be their percent error. However, there's a little bit of a weird thing going on with the sig figs here. When I subtract, what do I count? Decimal places. So how many decimal places in the first one? 1 decimal place. How many in the next one? 2 decimal places. And then over here, we're dividing, right? So it's kind of a different idea. We're not really looking at decimal places in the division. So when we subtract, we actually are only supposed to record how many decimals? 1. So it's not 0.36 as we said earlier. It should be 1 decimal. But we're not going to round that because I don't want rounding error. This is not a final answer. So it should be 1 decimal. So it really should be 0.4. But we're going to divide that by 8.9, which is we divide 1 decimal, which is only going to have 1 sig fig, divided by this guy with what? How many sig figs? 2 sig figs. Who rules the roost here? 1 sig fig. So this actually should be only to 1 sig fig. So what would that be in 1 sig fig? Just 4. Just 4% error. So that's how we kind of follow through those sig fig rules on percent error, which was which should be a question you're now going to be familiar with. Okay, and then someone started asking me, where's source of error? I'm not sure where we potentially went wrong or where there could be some error that I'm not aware of. So I want you to try to come up with 2 with the person next to you. Go. It can be anything in the lab. Sources of error.
Filling up your graduate, so is there too much or too little?
All right, I'm hearing a lull here, so I think you've maybe exhausted your possibilities. Somebody from this region, give me one. Give me one source of error. Okay, so what's wrong with the scale?
Like if you didn't zero it before you.
Okay, so that could be a source of error. I try to eliminate any like human stupidity from error, because an error is not, oh, I miscalculated or I read the ruler wrong, or I misused the equipment, because that's on you. Your human error should not be a part of experimental error, because you have complete control over you, right? But you may not have complete control over the scale, which who saw the scale fluctuating? You kind of had to like look at it like, okay, it's 3.0. Like you had to have those fluctuation debates within your mind. So the scale fluctuating, I would say would be an experimental error, because you can't control that scale, but you can control zeroing that scale. So I would never include that. All right, so this next group here, you 8, give me another potential. It's okay if you're wrong. We all learn from your mistakes and my mistakes and everybody's mistakes. Give me a thought.
Not bad.
Okay, so if the ruler was miscalibrated, maybe the ruler was, the centimeters were not actually correct, you could say error in the equipment. Okay, so you don't have complete control over that. That would be on me, but most of my rulers are pretty good, I'll say. Okay, so the next group, yeah.
How do we use one of the large graduated cylinders?
Okay, so the large grad sills, what was wrong? Well, I'm not gonna say what was wrong, but what was a disadvantage of using those?
They counted by 5, so you couldn't get one to be decimal.
Right, so they had larger differences in graduations. So you got less sig figs or less accuracy there. And that definitely could be something that you don't have control over. The frog could not fit anywhere else. They had to fit in the big one, and you kind of have to do more guesswork there than I would want you to do. So that's a good one to think about, is how good is your equipment. Last group over here. I know, save the best for last year.
Maybe part of the thing is like you're measuring, like maybe part of the wood was used was chipped off.
Okay, so malformations or malformed objects. So if you had a regular object and you're like, I'm assuming it's a perfect cube, that assumption may not be correct. So maybe like a chipped portion or like a sloped section could lead to different volumes or masses. Good, I didn't actually think of that. Another thing I'll consider just for the group is water temperature can change the density of water. Delta means change. And so if you change the density of water, I saw some of those floaters, those plastic pieces were floating, right? Yeah, and so you had to make the assumption, like, what volume did this change by? That assumption could change if you had different temperatures of water, hot water, cold water. That little plastic piece may have sunk, or it may have been more in the middle, which would cause error in our measurement. So those are some good concluding remarks on your lab. So the last thing I'll ask you to do is watch a quick video with me, okay? So if you would, please pass up your labs. We'll pass them all the way over to Cole, up and over to Cole. Just make sure your name's on it. And if you're a Ryan, put your last initial, please, since there are 3 Ryans in the room. All right, and labs should be passed up and over to Cole in like 30 seconds or less, please. You good? You have a question? All right, and last call for Cole. And after this, we'll watch announcements. Hopefully, Ms. Prada has it. All right, last call, and I am done taking labs. Thank you, thank you. Okay, I'm going to ask for you to pass through. All right, so what you'll notice is under, if you've not signed the safety contract, No, it is still up here. I don't erase things if they're here. I have a couple of you guys who need to do that. So if your name's on the board, if your name's on the board, you need to make sure that is done. Okay? 2, go and put the box for you ready. 2, homework for tonight, Monday. Maverick, what's homework for tonight? Can you see that? Sorry, in the back. Okay, so if you have more questions, text me or come to tutor after school on PS3A stuff. Reading guide chapter 1. And where would you find reading guides? So I actually printed out the first 3 reading guides for you, which is in your possession. But let's say you lost that paper. Under documents, there's a link to all the reading guides for the entire year. So I'm going to actually watch this video with you now so you don't have to do this at home. So it's a 4 to 5 minute video on it's Chem Collective one. And I want you to write down a couple of details about what this video is talking about. It's something called dimensional analysis. Okay, so dimensional analysis. That's not it. 4.5 minutes. Here we go.
Geometry provides a set of tools.
All right, you ready? Just write down a couple of facts on dimensional analysis.
Stoichiometry provides a set of tools that chemists use to manipulate quantities of substances. In working with chemical quantities, it is important to remember that each quantity has associated with it both a unit and a chemical substance. And it is important to always write both of these down. So, for example, we will write 4.1 kilograms of water, or 0.23 moles of oxygen, or 3.0 times 10 to the 21st atom sodium. Dimensional analysis provides us with the tools needed to convert between different units of measurement. Let's say we have the definition. 1 kilogram is equal to 1,000 grams. We can take this definition and form a ratio. 1,000 grams over 1 kilogram is equal to 1. And the inverse of that, 1 kilogram over 1,000 grams is equal to 1.
So basically he's saying, like 1 year equals how many days, right? How many years, or how many days? Approximately 365. So 1 year is equivalent to 365 days, so those are the same thing. So when you stack them as a ratio, the same over the same equals 1. Same way, the same over the same equals 1. This is called a conversion factor. It's like a fraction. It's a factor.
Ratios are useful since they allow us to convert from quantities in grams to quantities in kilograms, and vice versa. Consider, for example, the quantity, 4.1 kilograms of water. And say we want to convert this quantity to grams of water. We begin by writing down our initial quantity of 4.1 kilograms water. Next, we multiply the ratio 1,000 grams water over 1 kilogram of water. Remember that above this ratio was shown to be 1, so we are just multiplying our initial quantity by 1. This multiplication does not change the amount of water. It merely changes the units we are using to describe this amount of water. This multiplication gives the value 4,100.
Oh.
To determine the units of this quantity, we cancel the kilograms water and are left with grams water. So we achieved our goal of converting the quantity 4.1 kilograms of water over to that same amount expressed in grams of water. Let's do another example of a unit conversion. Say we are given the density of water as 1 gram of water per milliliter of water. And we want to express this in units of grams of water per liter of water. For this conversion, we will need the definition that 1 liter is equal to 1,000 milliliters. We begin by writing our initial quantity. Our goal is to convert the units of the denominator from milliliters of water to liters of water. We can do this by multiplying the ratio 1,000 milliliters of water over 1 liter of water. From the above definition, we know this ratio is equal to 1. So this changes only the unit of quantity, not the quantity itself. The multiplication gives the value of 1,000 and units of grams of water per liter of water. So we have achieved our goal of converting the density of water from units of grams per milliliter to units of grams per liter.
Okay, so essentially, and they didn't show the cancellation here, dimensional analysis involves all these units, and the units have to cancel at times. So if a unit is on top and a unit is on bottom, they can cancel each other out because they're countering each other. So what unit in this whole math right here, all this math work, what unit do you see also on top and bottom? Milliliter and milliliter, right? So the milliliters and milliliters cancel out. What is the only unit left remaining on the numerator? Grams, which is why it's recorded as grams, and the only unit left in the denominator. Liters, which is why it's also carried over to liters. So I'm going to show you one more example here.
A particular useful unit in chemistry is that of the mole. The mole is defined as Avogadro's number of items, where Avogadro's number is often abbreviated as Na and has the value 6.02 times 10 to the 23rd. So the definition of the mole can be written as 1 mole equals 6.02 times 10 to the 23rd items. This unit definition gives us the ratios. 1 mole over Avogadro's number of items equals 1, and Avogadro's number of items over 1 mole equals 1. Let's say that we have 0.43 moles of water, and we would like to convert this to molecules of water. We begin by writing down our initial quantity of 0.43 moles water. To convert this to molecules of water, we multiply by the ratio, Avogadro's number of water molecules per mole of water molecules. The multiplication gives the value 2.6 times 10 to the 23rd, with units of molecules of water. So we have achieved our goal of converting our quantity from moles of water over to molecules.
So if you can't see this bottom one, I might perk your head up. Can you guys see there's a mole here, molecules, which is different than moles, and then mole. What unit should cancel here? Right, moles on top, it's a numerator, and moles on bottom is a denominator. So those are canceling, leaving us only with a unit of what at the end? Molecule. That was just a baby intro. Baby, because tomorrow we're going to do more, okay? So I'm going to pull up announcements. And the other video is optional at this point. I got what I needed to show you. Mainly I want to give you a quick visual so that as we go on tomorrow, you're in good shape. Yes, Hannah? Yes. All right. They may not have announcements up here.